Hi, welcome to the next in our series of Practical Electromagnetics for Engineers. Today we're going to be covering Faraday's law, which essentially relates the electric and magnetic fields. So it essentially provides a way for us to think about both electric and magnetic fields. It also is going to break our condition of static electric fields and static magnetic fields, or fields that don't change with time. And we need to do this in order to really understand inductance, even though inductance is often considered a magnetostatic phenomena. If you're following along in the textbook, the first part of Chapter 6 is what we're going to be talking about today. So let's quickly review both the relations between electric fields and the relations between various ways to represent magnetic fields, since we're going to be talking about their coupling. We know that for electric fields we have a triangle that relates the charge, which generates the electric field, with the field and flux terms, which are related by the permittivity, and also the potential energy of a charge in a magnetic field, which we commonly call the voltage. And this triangle here we call our electrostatics triangle, gives us the mathematical relationships to convert charge to field or flux to voltage and whatnot. Although these are all vector expressions and they look fairly complicated, the math is relatively straightforward for some cases. We have very similar relations for static magnetic fields. Again, we have a triangle relation. But instead of charges generating the magnetic field and the magnetic vector potential, current elements do. So current elements, as we've seen, just replace the charges as the generating elements. And because currents have directions, these relations are a little bit more complicated. Most of the integrals will contain cross products, so the math gets a little bit hairier to do. But the idea is really very similar, as it should be, because we saw that magnetic fields are really just electric fields in the case of moving charges due to Einstein's special relativity and the contraction of space. So there really isn't that much difference. It's not like they're two completely separate things. We just treat them separately mathematically. We also saw that there was no magnetic charge, that because magnetic fields come in loops, there's not a magnetic monopole, a positive and negative magnetic charge that we can separate. We'll never find those types of things. So what we're really interested in doing is looking at both the electric fields and the magnetic fields in a more holistic way to see how they're related. So here I've drawn both triangles on their sides. Here's the magnetic side, it's green, and I've drawn a bar magnet to represent that and a little lightning bolt for the electric field case, or the electrostatic case. And I've put our relationship that there aren't magnetic charges in the middle of this, since we need to remember it, and you can essentially ignore that over there. That's just a typo. And the way I've drawn this is to show that there should be a relationship between the two generating elements of charge and current. And if you think about this for a second, you see that the thing that relates charge and current is that current is just the rate of change of charge. Because charge is conserved, you don't destroy it. It has to go somewhere. It has to flow. So current essentially is the flow of charge, the movement from one place to the other. So the two things that relate these triangles is, in fact, time. That things that change in time, charges that move in time, give rise to currents. And so you would expect there to be relations between electric fields and magnetic fields. And what we're going to be talking about today, Faraday's law, is how some very, very smart people figured out this relationship, which wasn't done overnight. It took years and years to understand these relationships, but we can look back on their wisdom and, as they say, stand on the shoulders of giants to try to do this fairly simply. And the way we're going to do this is we're going to think about a loop of wire that moves in a magnetic field and try to extract some relationships from there we can then build on to really do a more mathematical relationship that in fact will combine our magnetostatic or non-changing magnetic fields with our electrostatic or non-changing electric field pictures we've developed to date. So what we're going to do is we're going to do what's called a thought experiment. This is an experiment that would be very hard to set up in real life, but that we're going to essentially do on pencil and paper so we can think about this and understand it. Essentially what we're going to do, as I said, is we're going to move a loop of wire through a magnetic field. The magnetic field is represented by these greenish arrows, and in our thought experiment we're going to say it's only in sort of the square region given by this green square right here. So wherever you see that green square, there's a magnetic field. That magnetic field is pointing straight up in the y direction. And the loop of wire is moving in the xz plane, and it has velocity in the plus z direction. So it's moving in plus z, and so it's going to come scooting along here, and at some point it's going to intersect the magnetic field. And because I'm not a very good artist, even when I'm using a computer, we're going to essentially do a two-dimensional view of this. So imagine as you look at this figure over here on the left that we're going to sort of rotate our perspective till that y-axis is pointing straight up at us. And so here's our y-axis. We're looking down from the top. So our magnetic field B is pointing out of the screen at you. And be careful because that y-axis will poke you in the eye if you get too close. Remember that we're going to be talking about magnetic flux. And we define the magnetic flux to be the total amount of the flux B going through an area. So we just basically sum up all the flux arrows B that go through some area, and that gives us total magnetic flux. And we're going to be calculating the magnetic flux that goes through this loop. And so I'm going to be looking at two quantities here. I'm going to use blue lines to represent the flux. And I'm going to be plotting the flux as a function of time as this loop moves into the magnetic field. And I'm going to be using red lines to calculate the current, I. So you know my color scheme here. We know that this loop is going to be moving in the plus z direction with some velocity vector v. And what I'm going to do is we're going to plot the flux and the current before the loop has moved into the magnetic field. So here's our magnetic field B, and remember that's pointing straight up at you because we're looking down from the y-axis. And so if I do this plotting, the flux before the loop has entered the field is 0 because none of the magnetic field lines are going through there, and because we can't move a loop through space and get a current out because that violates conservation of energy, there's not going to be any current flowing in this loop either. Things change, of course, when the loop starts to enter the magnetic field region. So remember, our loop's moving down in that direction, and it's just entered the region of magnetic field B down here. We know there's going to be a force on the electrons in the wire. Well, there's also going to be a force on the positive charges, but they're not allowed to move. And we know we can represent this force as being equal to negative E, which is the charge on the electron, the velocity vector crossed with our magnetic field. And at this point, you need to take your right hand and you need to point it down toward the bottom of your screen because that's the direction the velocity is in. And then you need to rotate your fingers up so it's pointing out of the screen at you. And you'll see your thumb is pointing over to the left side of the screen. But because of this negative sign right here, we know the force on the electrons, and so let's write that F sub E, is going to be pointing to the right. Because we know the current flows the opposite direction from the electrons, because of course the electrons are negative charged, our current is going to flow over to the left, I, that way. And because this is the only force on the electrons, the only thing that's generating current, we essentially see we're going to try to drive current in the clockwise direction, I, going this way, around the loop. So if we go ahead and plot the flux, we had 0 flux before we entered the loop, but now our flux begins to increase at a steady pace because our velocity essentially is constant, and so the area of the loop that intersects the magnetic field simply increases linearly. The current, on the other hand, turns on very suddenly. Now, is a current going in the clockwise direction a positive current or a negative current? Again, you use the right-hand rule. You sort of curl your fingers around in the direction the current's going, and if you do this with your right hand, you'll see your thumb is pointing down into the board, and so the current essentially corresponds to a negative current. It's pointing away from us. And so essentially what we're going to do is we're going to see that the current turns on very, very suddenly. And it turns out that something else happens here, because we know as soon as you have a current flow, there's another force. And that force is I, the current you generated, dl, which is the direction the current's flowing, cross B. And so if I take my I, which is basically pointing over in the negative x direction, this way right here, put my fingers of my right hand that way, cross it up in the B direction, so the fingers are pointing out of the screen at you, there's another force on the loop, and so let's call this F sub L, that's pointing away from you. So as soon as this loop enters this region of magnetic field and induces a current, the loop pushes back at you. It does not want to go into this region of magnetic field at all. And this actually makes sense in a way, because we can't induce a current and do work for nothing. The force is opposing us, and we've got to push this thing, actually physically push this loop into the field, and this is just due to conservation of energy. And it turns out that the fact that it pushes back in the direction it pushes is known as Lenz's law. And we've just derived it right there. Okay, so let's go to some point later in time. Our loop is continuing to move into the magnetic field. So if we think about our flux, it turned on suddenly, and it's continuing to increase at a fairly linear rate. At this point, most of the flux has gone in there. What about the current? Well, we're still getting essentially a current flowing in this direction, in the counterclockwise direction, because the electrons are being pushed counter to that arrow right there. But are the sides of this loop going to contribute any current? Well, it turns out that the force on the electrons is that way, the current would be that way, and we can't induce a current going sideways in a wire. You might actually get some separation of charge in the wire, which technically is known as the Hall effect, but we're not going to go into that. But you're not going to induce any current from the sides of the wire because the electrons don't really have any place to go. So if you think about how the current behaves, it starts as 0, it went negative, and it's going to stay pretty constant as the loop goes into the wire, even though the flux is increasing. Our loop continues to move down at constant velocity, but now the loop's completely inside the region of magnetic field. So if we think about our flux, it started at 0, it started to increase. At this point in time, it's constant because the flux isn't changing, but it does have some positive value. What happens to the current? Well, we know that there's a current going this way that's induced by the leading edge of the wire as it goes down, but the trailing edge of the wire is also going to feel exactly the same force, and so it's going to have a force on the electrons, and it's going to try to put a current that way. What happens when we have two wires of equal length both trying to force a current in opposite directions? It turns out that at this point the current drops to 0 because the forces balance each other out and no current's being forced through the wire, at least assuming this little section is so small we can neglect it. So if we plot the current as a function of time, it turned on, it went negative. As soon as that loop entered, it dropped back down to 0, and it stays 0 as long as the loop is in there. Because there's 0 current, now the loop can move freely. There's no force opposing its motion at this point in time. Let's go on and think what happens when the loop begins to leave. Well, at that point, there's no force on this side of the wire whatsoever because it's exited the magnetic field. It's just moving through space. However, we still get a force on the trailing edge of the wire. We know the force on the electrons we calculated before is in that direction. We know our current essentially is going to be in that direction, and so we're going to have a clockwise going current. If you take your right hand, curl your fingers along the direction of that arrow in the clockwise direction, you'll see that the current in this case has changed direction. It's positive. And so if we think about the flux, it was 0, it turned on, it stayed constant, and now it's starting to drop at a steady rate. The current, on the other hand, was 0, went negative, turned off, and now is starting to go in the positive direction as the loop leaves the wire. Again, we can look at Lenz's law, and we're going to see that the force on the loop essentially is trying to go that way. It's trying to keep the loop inside the magnetic field. It does not want that current to be generated. So we've got to, again, push the loop out of the magnetic field. Again, this is just conservation of energy. You can't generate a current for nothing. If you could, our energy crisis would be solved at this very instant. Moving right along, our loop keeps moving down in that direction. We've almost exited. At this point in time, we still have forces on the electrons pushing the current in that direction. We still have a current going that way. But essentially what happens is we're almost out of flux because the loop has completely exited. We're here. We're down at that point right now. The current stays constant, again, because the sides don't contribute. So if we look at the current as a function of time, we're going to get a function that looks like that. And if we go to the next point in time, so that the current has completely exited the loop, we can complete our drawing and say that we now have 0 forces. There's no current in the loop whatsoever, no forces on the electrons in the wire. If we look at what the flux has done, we see it's increased, stayed constant, decreased, and now turned off. The current, on the other hand, went negative, went to 0, went positive, stayed on, and as soon as this loop exits and there are no more forces on it, the current drops to 0. Again, that makes sense from conservation of energy. So if we go ahead and plot this, here's the flux. It goes up, it stays steady, it decreases, it turns off again, and we plot the current, which goes negative, turns off, turns on, turns off, we see something interesting. We see that the current is related to the rate of change of the flux. In fact, when the flux was increasing, or the slope was positive, the current was negative. Similarly, when the slope of the flux was negative, the current was positive. And so we can write this in this form right here, because it turns out that it's not the current that's generated, and this was verified experimentally. The current is actually generated by a voltage around the loop. So Faraday's law essentially states that the voltage around a loop is equal to the time rate of change of the flux, and of course we can just write the flux as the time rate of change of the magnetic field. Let's do another thought experiment and change this. Instead of moving the loop, let's just keep our loop fixed in space as shown in this diagram right here, and we'll make the magnetic field be a function of time. In other words, what we'll do is we'll turn our magnetic field on slowly, leave it on for a while, and turn it off. Then if we plot the flux, before we turn it on, the magnetic field or flux of the loop is going to be 0. It's going to increase, it'll stay steady, we'll slowly turn it off, and not move the loop at all. Faraday essentially tried to do this experiment, or an analog of it, and he essentially found that you get exactly the same result. It's not the motion of the loop per se, but it's the rate of change of flux that induces a voltage around the loop. So again, we express Faraday's law as this: the voltage around a loop, and there can be a wire or not, but an induced voltage is equal to the time rate of change, or the negative time rate of change of the flux, which is given by the surface integral of the magnetic field. Now we use some of our vector calculus identities. We remember from electrostatics that the voltage essentially is the integral along some path of the electric field. That's our definition of potential, in fact. Around a loop, we simply put this little circle on the integral sign to say it's a closed loop. And then, in this case, the voltage around the loop we can write as this integral, and we set it due to Faraday's law as equal to the time rate of change of the magnetic field. And now we find something interesting. When fields are changing in time, our old relationship that the line integral of an electric field around a loop is equal to 0 is no longer true. We find that this, in fact, is violated. And so one of the rules we've based things on has changed in the case that we don't have static fields anymore. Now, we know we don't always like to work with integral expressions. When you're given a particular geometry, integral expressions are great, but when you have sort of a more distributed field, you like to use differential expressions. They're much easier to calculate. And this is where Stokes' law, remember Stokes' law comes into play here. And Stokes' law says that a vector field measured around its perimeter is equal to the rate of change of the curl of that field over the area that the loop creates. There's Stokes' law right there. And so we can essentially replace this E dot dl with del cross E. When we do that, we have a differential distributed expression right there if we just basically cancel the surface integrals. And that is the curl of the electric field is equal to the negative rate of change of the magnetic flux vector B, or the magnetic flux vector B. This is a very important expression, and we'll come back to it later. And it essentially comes from Faraday's law, which is the experimental observation that when you change the magnetic flux around a loop, it induces a voltage. Faraday's law right there. And so with this thought experiment, we have done a formal relationship between the two triangles. We see that, in fact, time is what relates the electric and magnetic fields, or electric and magnetic quantities in a more general sense, and that Faraday's law, which can be expressed either in an integral form or a differential form, relates the magnetic fields and the electric fields. So we formally combine the two triangles through Faraday's law. Now, I won't go into all of this, but it turns out that when we combine the triangles, when we have fields that are changing in times, a lot of the electrostatic equations that we determined and a lot of the magnetostatic relations we determined are no longer accurate. All the ones that have red X's through it now don't hold when you have electric and magnetic fields that change in time. There's good news and bad news to this. The bad news is that we learned a whole lot of stuff that's not useful to us anymore when fields are changing in time. They're only good in the static case. The good news is we have a whole lot less expressions to remember, and the expressions we do have look a lot simpler. So the next set of lectures is going to look at what happens when fields change in time and some additional simplifications we can do to understand this and to understand how energy propagates through space.